Yeah, please.
Yes.
Thank you, Professor Zhang, for your excellent presentation about your job in reinvent the transistor. Very good one. Thank you. You know, you introduced that you use selective capacitor to improve the memory speed of the transistor. I wonder whether the FT or Fmax of this transistor can be improved in the same way.
Yes.
For example, by 1,000 times, so that a conventional.
Not 1,000 times, but I believe we can improve maybe 2 times, 3 times, or more.
Yeah, for example, the FT of a transistor,
Yes.
the 65 nanometer of TSMC can operate at about 100 gigahertz or something. If we make use of the selective, it can go to about 1 terahertz or something like that.
Not very 1 terahertz, but we believe that we can. You know why we can make a higher frequency, or 5x max, or 5f max or FT? Because by using negative capacitance, we can reduce the straight capacitance and the resistance. So combine reducing straight capacitance and the resistance. RC constant is much lower. So we are not doing it that. We are thinking about that. We will demonstrate in the next or near future. We will demonstrate that. We will demonstrate a much higher Fmax and FT. We are looking forward to do it.
Okay.
Your comment is very exciting to me. We are going to do that. Yes, I hope we can do it, and
Okay.
we'll demonstrate in the next presentation.
Okay, thank you very much.
Thank you.
I have a second question.
Yes, please.
Sorry. It is possible to use inductor instead of the selective capacitor for this similar
I
function.
consider that. This is a negative capacitor. Is negative is equal to inductor? I think about it before, but sounds that it's not really true. It's not really an inductor. It's different. So because inductor cannot make this kind of polarization curve, but we can make it. So this kind of polarization curve versus energy is a proof of negative capacitance. But inductor cannot do it. So I think it's different. In a circuit theory, maybe it's something working like inductor, but it is not.
Thank you.
Yeah, there are questions. Yeah, please. Yeah.
Yes.
Yeah.
No, very nice talk.
Thank you.
My question is, essentially the ferroelectric has been studied for many, many years.
Yes,
And
many
also
years.
tried for the transistor.
Yeah.
But the key, I think previously the key point was that his endurance actually was limited by about 10 to 12.
Yeah.
But why now you have about 10 to 16? So what is the secret?
I don't know.
I think this is the key point.
We did demonstrate it, but I don't know why. But I don't know why. But I don't know why. But we did demonstrate it. Yeah. Maybe I go back. I study in tips. Yeah. I think there are some key points there. You are right. Yeah. We should do something more in the future. Yes.
Mr. Lin? Yeah, please.
Hello. Thanks, Professor Chang. It's very enlightening, and I'm very glad to
I'm very naughty.
I'm very happy that more law is overflowing. Very good. In my experience with semiconductor as a commercial product, I own a company in semi before, way back. And we were doing 90 nano and everything in the year 2000. The cost is not in semi, the cost is really in packaging.
Yeah.
And in order to really support this kind of so advanced semi, you really have to have a comparable packaging to use it. Otherwise, it's very hard to really benefit from such a high tech. So my question is there a parallel path to work on packaging so that you can put in an iPhone and all those commercial products?
Yeah, your comment is very important, but very exciting thing is that TSMC is now suffering from, because the density becomes so high, suffering from heat issues. Heat issue. Heat is a very significant things in their future. And they come to see me, so you say, maybe it's possible to solve the heat problem because my solution is providing a very low power consumption. Very low power consumption. So TSMC is very eager to have our cooperation to solve the future problem because heat is the main issue for the future generation of FinFET. Nowadays, 10 nanometer still suffering from heat issues. For 7 nanometers, even more serious. 5 nanometer, even more serious. So this is a key issue. We should solve the problem, and they found that this maybe our solution is one of the solutions they can provide them to work on the futures. So we are very excited to say we can do something for them. But I don't know the real thing is coming out or not, but we try to do that. Principally, it's okay, but we need to do something real and demonstrate. It can really solve the problem. Still, I don't know, but we want to do that. It's very important, yeah. Heat issue is most important issues. But the only way is to make it in a low power consumption. It's very important. And the power consumption depends on VD. VD reduce 10 times, then you could do power consumption 100 times. VD square. Power consumption proportional to capacitance, frequency square, and the VD square. So the increase 2 times of frequency, you increase power consumption 4 times. So something like this. So I think it's important. Maybe one of the solutions to solve the problem in the future. Thank you.
Another question? Oh, I have one question.
Yes, please.
Yeah. So it seems the level of internal stress of residual stress is very important in the stranded stranded nitride.
Yeah.
So what's the ideal situation for this so-called strain or stress inside of this layer, or when you have a 3D structure, how you manage it, and how we can predict the stability or relaxation of this strain, a change of this strain during the cyclic loading.
Yeah, we are not doing the reliability issue, but I think in the future, reliability will be the key issue for this kind of device. Still, we are not solving all those problems, but I think you're right. Reliability is the most important issue in the future. If it can be used in real production or not, it's a key issue.
Yeah, my question is about the level distribution of the strain inside of the stranded nitride.
Yeah. If a strain release, then you cannot keep the real good crystalline structures.
Yeah.
Yes,
Okay.
something like that.
I see. Okay.
So strain maybe is not a good solution for reliability.
Okay.
If you relax, then you do everything.
Yeah.
Yes.
Okay.
Yeah, thank you.
Any other question? So if not, let's thank again Professor